Once we have selected the proper adhesive, it's time to characterize that adhesive, to know the strength properties, the fracture properties. This will be useful later for joint design.
We know which adhesives exist, we know how to select them. Now it's time to characterize them, to know which are their mechanical properties. This is especially important for joint design that we will see later. So in this module I want to see with you the different types of tests, mechanical tests, to have the mechanical properties of these adhesives. The first test is the tensile test. This is part of the strength test. We can divide the test into types. We have the strength tests that will give us, like the name indicates, the strength, the ductility, the modulus, and then we have the fracture mechanics test that will give us the fracture energy. And starting with the strength test, the most important one is the tensile test. Very easy. You use a dog bone specimen of the adhesive itself, all right? We have here of different types. This is a film adhesive, actually. One of the film that we have seen in the previous module. And you put it in the tensile machine. You can use the load cell to determine the load, and for the displacement you can use an extensometer, which is a contact measurement device, or a video extensometer, which is better, that influences less the behavior of the adhesive. And you get this type of result: stress, tensile stress versus tensile strain. And this is the stress-strain curve of the adhesive. You can get the modulus, the strength, and the ductility. If you use the metals, that would be over. You could deduce the compression or the shear from the tensile test, but for polymers it's a bit more complex. So you need at least another loading mode. It could be compression, but compression is quite difficult. In general, we prefer shear. And one of the most common type of tests is the thick adherent shear test. Thick, like this specimen, you can see, thick to make sure that there is no peel in the joint. It's purely loaded in shear, the adhesive that is in here between the two substrates. So we load this like that, we measure the load, we measure the displacement in the adhesive, which is shear, which is not easy. There are special devices, non-contacting devices, to measure the displacement in the adhesive, and then you can generate the shear stress, shear strain of the adhesive, and get the shear modulus and shear strength and shear strain, like in the tensile mode, but this time for shear. So that's the two main tests in terms of strength tests. Now for the fracture energy. One of the most common type of test is the DCB test, the double cantilever beam test for mode 1 fracture energy. I can show you various specimens. You have this one, this is very common. This is aluminum alloy used in aerospace. You have these two holes, and then you would load the specimen like this, and you would apply this mode of loading, which is mode 1. If the specimen has a substrate very thin, you can put these shims and make a hole, and then you load it in some way. If you use composite materials, which is the case of this specimen, you can also bond something like that, or you can use also piano hinge. It's also very common. Okay, this one has already been loaded actually. Okay, it's already broken, but there are various geometries. And the objective of the test is to get the fracture energy. One way of analyzing this is looking at the total potential energy of the specimen, which can be seen as the difference between the stored elastic energy and the total energy from the external forces applied, this load here, times this displacement. So you are left with this for the total energy of the system. On the other hand, the displacement can be written as a function of the compliance and the load. Compliance is the opposite of the stiffness. The displacement can also be obtained from the beam theory. So you also have an expression for the compliance as a function of the crack length. Then this simplifies like this, the total potential energy, and at the end you have this expression. By definition, the strain energy is the variation of the total energy as a function of the area, width times the variation of the crack. This can be also the variation of the compliance as the variation of the crack, and at the end you have this. The critical value will be that corresponds to the propagation of the crack for the maximum load. But in any case, really, if you want to get the fracture energy, you need to measure during the test the fracture or the crack length A, which is not always easy. In mode 1, not that complicated because it opens, but imagine that you want to test this in mode 2. You apply typically bending, then the two arms will be against each other, and it's very, very difficult to detect the end of the crack tip. So one thing that is commonly done is to use another data reduction scheme, which is the compliance-based beam method, which deduces the crack length from the measurement of from this displacement. There is some mathematical treatment involved, but it's not that complicated, and you can actually get the fracture energy without even looking at the crack length, which is very powerful data reduction scheme. So we have seen the strength test, we have seen the fracture energy tests. What about the environmental conditions? Does it make sense to test at another temperature, or it's enough to test at room temperature? No, we are talking about polymers, don't forget, and polymers are very sensitive to temperature variations, water, etc. You have here an example of how an adhesive changes its strength, strain curve. How does it change with temperature? We have here room temperature, but look at -55, it gets stiffer and stronger, but less ductile. And as temperature decreases, the strength decreases, ductility increases until you are over Tg. Tg for this adhesive is about 150 degrees, glass transition temperature. So I remind you, a structural adhesive is only structural if it's used below its glass transition temperature. So really, if you want to design, taking into account temperature variations, you need to test at different temperatures. Will the adhesive be in contact in water? Yes, then you need also to understand how the properties of the adhesive will change with the absorption of water, and it will change a lot. Again, stress-strain curve, this is without water, and after periods immersion in water. You can see that the strength decreases and the ductility increases. It's not too bad actually. And if you don't exaggerate and you don't create chemical damage, you can go back to the beginning if you dry the adhesive. Physical damage is reversible. And finally, the strain rate, it's quite important. When you have an impact of a bird in a plane, then the loading rate is very high, and you should know how the adhesive behaves in such conditions. To show you that really it matters, you have again a stress-strain curve. This is for 1 millimeter per minute. It's exactly the same adhesive, and this is for 100 millimeter per minute. So really a big difference when the strain rate increases. It's another galaxy. And that concludes the module. Again, we know how to characterize the adhesive, strength tests, fracture mechanics tests, and we know how the environment influences the properties. And if we want a complete, rigorous joint design, then we should take these environmental factors into account.